Good morning, Year 9, and welcome to another online lesson. This one, as you can see, is called Reversible Reactions. So this lesson, hopefully by the end of it, you'll be able to describe the energy transfers in reversible reactions. To start with, though, I want you to answer 6 questions for me. What does that sign mean? What is a reversible reaction? What happens in the thermal decomposition of ammonium chloride? Name 4 factors that affect the rate of reactions. Does concentration increase or decrease the rate of reaction? And does increasing temperature affect the rate of reaction? So pause the video now and have a go at answering those questions for me. So I hope you've managed to answer those questions. The picture on the right, as you can see, basically what's happening is we are heating ammonium chloride to above 340 degrees Celsius, and so the white solid ammonium chloride will thermally decompose into a mixture of 2 colorless gases, which are ammonia and hydrogen chloride. And then on cooling the reaction down, so when it cools down, the reaction's reversed and you get solid ammonium chloride reforming. So that's an example of a reversible reaction. So hope you've answered those 6 questions. Here are the answers I have written down. So that sign means that a reaction is reversible. A reversible reaction just means that the product can then make the reactants, and so can vice versa. What happens in the thermal decomposition of ammonium chloride? It will form ammonia and hydrogen chloride gas, and then on cooling will reform ammonium chloride. Name 4 factors that affect the rate of reactions: pressure and concentration, catalysts, temperature, and surface area. Does concentration increase or decrease the rate of reaction? So a higher concentration will increase the rate of reaction. So there's more particles, therefore more collisions, therefore more successful collisions, and therefore a faster rate of reaction. And then does increasing temperature affect the rate? Yep, it does, because increasing temperature increases the rate of reactions. Particles have more energy, which means more collisions will be successful, because more collisions will have that activation energy that's needed for a reaction to actually occur. So on to today's lessons. So we're talking about reversible reactions. So if you've got reactants A plus B and they form product C plus D, you can then reform the product, the reactants A plus B, and then it can keep going around in a circle. That is a reversible reaction. So if in one direction, we'll say the forward direction here is the red direction, A plus B forms C plus D. If that is an exothermic reaction, so it will be transferring energy to the surroundings when it goes in that direction. And so if it's an exothermic reaction in one direction, the reversible reaction, or the reverse of the reaction, will be the opposite. So in this case, endothermic. So it will then take in the exact same amount of energy from the surroundings when it goes in this direction. So if A plus B starts with 100 joules of energy, in the reversible reaction at the end, when it remakes A plus B, it will have 100 joules of energy again. So even if it loses 50 joules of energy in an exothermic reaction, it will then have to gain 50 joules of energy again in the reverse in order to remake the product. So in any reversible reaction, the amount of energy transferred to the surroundings when the reaction goes in one direction is exactly equal to the energy transferred back when the reaction goes in the opposite direction. So can you please make sure you've got that fact written down? I like to also draw the arrows and the diagram at the top right. and then labeling one exothermic and then one endothermic. So one more time, if A plus B releases heat when it forms C plus D, that's an exothermic reaction. So it's transferring energy out of the chemicals. And so in order for it to be a reversible reaction, it needs to take in exactly the same amount of energy that it released. So it will be endothermic in the other direction. So we talk about forward and reverse directions in reversible reactions. So hopefully you've got that definition down and that diagram. So these are what the energy profiles look like, the reaction profiles look like in these diagrams. So on the left, an exothermic reaction. So we have our reactants, and then they will take in a certain amount of activation energy, and then because it's a exothermic reaction, it will end up with less energy than what it started with. So that is an exothermic reaction. And then if you see, they are exactly in line, because then it will have to be an endothermic reaction in the opposite direction. So it will then form up here, so you're going to need more activation energy, but then it will reform those products. So those products will have the exact same energy as they started with. Okay, so this would be A plus B and A plus B, and this would be C plus D, C plus D. So one more time. So if we got reactants here, A plus B, they need activation energy in order for the chemical reaction to occur, and then they will release energy because they are an exothermic reaction. And so the products created, C plus D, will have less energy than what they started with. These letters A, B, C, D, by the way, they're just instead of using exact chemicals, just to make it a bit easier. So A plus B, then activation energy, and then it will release energy because it's an exothermic reaction, and its products, C plus D, will be less or have less energy. And then C plus D over here again still, so in order for it to be a reversible reaction, activation energy, and so it needs to absorb that much energy so that the products A plus B are the exact same energy that they started with. And that is reversible reaction energy profiles. So make sure you've got those two diagrams down. If you don't, pause the video and do that now and write those two down. So this is just kind of an example of a reversible reaction. So when hydrated salts such as magnesium sulfate crystals are heated, the water of the crystallization is driven off, leaving the anhydrous salt. So the hydrated form can then be reformed by adding water. So on the left here, we've got magnesium sulfate, and it is hydrated. So if you see here, H2O, which is water. So it is magnesium, sulfur, and oxygen. And then joining that, we've got water molecules. So it's hydrated. Remember, if you say hydrated, so you need to say hydrated in summer when you get really hot. Same thing with these, hydrated. They've got water attached to them. So magnesium, sulfur, and oxygen, magnesium sulfate, and it's got water, so it's hydrated. When we heat that up, so we put it under a Bunsen burner, for example, it will break those bonds, and you'll be left with magnesium sulfate still, but it will not have water attached to it. So the water will have broken the bonds and not be attached to the magnesium sulfate. So we call that anhydrous, means without water. So that magnesium sulfate now doesn't have water attached to it. So this is an example of a reversible reaction, because what I can then do is with this magnesium sulfate, I can cool it down and add water back to it. And by adding water to it, it then becomes hydrated, creates those bonds again, and becomes hydrated magnesium sulfate. So it's a reversible reaction. We're heating it, and it's absorbing energy, so it's endothermic, and then cooling it, so it's releasing energy, and then it's hydrated magnesium sulfate again. So it's an example of a reversible reaction. The forward reaction is endothermic because energy is taken in. We're heating it on a Bunsen burner. And then the backwards reaction, this one down here, is exothermic because heat energy is transferred to the surroundings. So the amount of energy taken in is the same as the amount of energy transferred to the surroundings. So we're going to show you two experiments in a minute. We're going to heat copper sulfate crystals and heat cobalt chloride crystals, and it's going to be the same thing, but instead of magnesium sulfate, we'll have copper sulfate and we'll have cobalt chloride. So they're in one direction, they'll be coming anhydrous, and then in the reverse direction, they'll be coming hydrated again. So this is the experiment I'm about to show you. So I'm going to add a spatula of copper sulfate, or half a spatula of copper sulfate crystals. So CuSO4 5H2O. You will need to know that a bit later on because you'll need to write down the chemical equation. And I'm putting that into a boiling tube. I'm then going to use a test tube holder and I'm going to heat the blue powder in the Bunsen burner. So the copper sulfate is blue. And then I'm going to look at what color that copper sulfate comes when I heat it and what else is happening. And you can see it in the picture here. So what gathers on the outside of or inside of the test tube, so what's coming off it. And then I'm going to allow the solid to completely cool. And then I'm going to add some water and observe what happens to the color. So it's blue now, it's going to change color. And then what happens to that change color when I then add water to it. And I'm going to keep doing that back and forward. And then I'm going to repeat the same thing using cobalt chloride. So same thing again, but instead of copper sulfate, I'm going to use cobalt chloride and look at the color changes. Hi Nine, so here we're going to show you an experiment which is a reversible chemical reaction. So here we have some copper sulfate and then we're also going to test some cobalt chloride. Now we're going to talk about the copper sulfate first. So this copper sulfate, its chemical formula, this is a hydrated copper sulfate, so it's CuSO4 5H2O. So it's got water inside the copper sulfate. So as you can see, the copper sulfate is blue, obviously here. What we're going to do is we're going to add some heat, and then we're going to see what colour this copper sulfate turns. So whether it stays blue or whether it changes colour. Okay, so one of the key things with the chemical reaction is that a colour change will occur. So we are doing a chemical reaction here, and hopefully we should start to see a chemical change. And if you look closely, you can see that it is currently going white. So it's changing from blue to white. So I'm going to grab my test tube here. As you can see, you've got steam coming off the top. So it's just a chemical reaction, and the water vapor is leaving. So most of this is going white. As you can see, you've got steam, and then you've also got some condensation on the outside of the test tube here. So this is a chemical reaction, and it's a decomposition reaction, and it is losing water from the copper sulfate. So it's going from copper sulfate, so CuSO4 5H2O, and it is turning into CuSO4 plus 5H2O, but obviously we're not collecting the steam, it's just coming out the top here. So as you can see, it is white. So I'm going to turn my heat off for a second. So I've got my white powder here, as you can see, and then what I'm going to do is I've got some distilled water. So what I can do is add water to the anhydrous copper sulfate, or copper sulfate that didn't have water, and what you just saw there was a chemical reaction. And what I now have in the bottom of this test tube is blue again, because it is copper sulfate again. And we can just do the exact same thing again, and we can heat it up again.
I added a little bit too much water. What we can do is heat it up again, and we should get anhydrous copper sulfate again. So when we heat it up enough, lo and behold, we get a white liquid again, which is anhydrous copper sulfate. So we've now just removed the water again from the copper sulfate, and so it's now just CuSO4. Okay, it doesn't have any water in it, which is why it is white. And then again, because it is a reversible reaction, we can reverse the reaction again, and we can go from anhydrous copper sulfate to hydrous copper sulfate simply by adding water again. So one more time, add water, and it goes back to being a blue liquid again, or a blue solid. Okay, so we go from copper sulfate, which is hydrated, so has water in it, to anhydrous copper sulfate, so copper sulfate that doesn't have water in it. We're going to test one more. So we've got, just move this, we've got cobalt chloride. So this is technically already anhydrous. So it's cobalt chloride, and it's technically already anhydrous. So if we heat it, and keep heating it, see that color change there? So it is losing that water. So it was hydrous, and then if we let it cool down, again, it's very slow, and I'm a bit impatient, so I'm going to add some water already. We add some water, and it goes blue. So we've got blue, and then when we take the water off, it then goes purple, so then turns anhydrous again. It's the same thing again, it's that reversible reaction, okay? By adding energy or taking energy away, so either exothermic or endothermic, and we change that direction of the chemical reaction. So one way or another way, okay? There we go. And that is a reversible chemical reaction, okay? You can either add energy or you can take energy away.
So I hope you enjoyed that experiment. I certainly enjoyed doing that experiment. So now comes the fun part where you're going to need to try and answer some questions for me. So can you please explain what is meant by a salt, water of crystallization, a hydrated salt, and an anhydrous salt? If you're stuck, have a look online, try and find the answers to that. And then number 2, write a word equation and symbol equation to show the equilibrium between hydrated and anhydrous copper sulfate crystals. So you need to, if you're stuck and don't remember what copper sulfate hydrated is, the chemical symbols, jump back about a minute in this video and find copper sulfate hydrated and copper sulfate anhydrous there. And then 2, this is a really hard question, but I think you guys can do it. Explain in terms of bonds broken and formed why the forward reaction is endothermic and the backward reaction is exothermic. So think about the fact endothermic is absorbing energy, and then exothermic is releasing energy. And then think about what happens when things change states. Think about bonds broken and energy levels. Okay, how do we make bonds and how do we break bonds? What energy do we need to do that? And then last but not least, the last question is draw a labeled energy profile diagram for this reaction. So instead of writing reactants and products, you'll then write the actual thing. So copper sulfate hydrated, and then copper sulfate and water anhydrous. Okay, and you'll put that onto a energy profile diagram for me. So pause the video now and try all of these questions. They should take you about 8 minutes. Okay, hopefully you've managed to answer those questions. We are going to now mark them. So, when an acid is neutralized by an alkali, base, or carbonate or metal, the ionic compound that is formed is called a salt. So that's what a salt is. It's that ionic compound when you neutralize an alkali, a base, a carbonate, or a metal. Water of crystallization is defined as water that comes from a crystal substance after heat is applied. An example is the water that drips off of a water crystal as it warms up. So the other example is the copper sulfate. Obviously, when you heat that up, the hydrated copper sulfate, the water of crystallization is the water that comes off that blue copper sulfate that you saw in the video. In a hydrated salt, the water molecules are incorporated into the crystalline structure of the salt, and then anhydrous just means without water, which I said earlier on. So this is now the question about bonds and how bonds form and break. So where the energy from bond forming exceeds that needed for bond breaking, the reaction is exothermic. So it's exothermic backwards this way because you're releasing energy out. And so when you release energy out, you get bonds forming. And then when energy for bond breaking exceeds that from bond forming, the reaction is endothermic. So there's more energy going in, which means you break the bonds. So you form bonds when there's energy going out, you break the bonds when there's energy going in. Then your word equation you need to write down, endothermic in the forward direction, because remember we added heat, so took in heat and broke those bonds. So it went from hydrated copper sulfate to anhydrous copper sulfate plus water. So that is the word equation there. That should have a little S there for solid. That should have a little S there for solid. And that there should have a little L for liquid. And then obviously to exothermic go backwards. And then the energy profiles, you've got exothermic. So you should have written our exothermic reaction. So you should have written copper sulfate plus H2O. Oh, sorry, and that's anhydrous, forms hydrated copper sulfate, and then hydrated copper sulfate up there, and then anhydrous copper sulfate and water there. Because an endothermic reaction then makes a product of anhydrous copper sulfate plus water there. So those are the answers to all of those questions. So again, a few more questions for you to do. These are again very hard, so make sure you're pausing the video, looking online, looking at your notes and trying to answer these questions as best you can. If you can't answer these questions, just have a go anyway. All right, have a think. So pause the video now and answer these questions. Okay, hopefully you've answered these questions. So here are the answers. So the paper, it's sensitive to humidity and it turns from blue to pink if water vapor is present. So then we need to keep it in that machine in order to keep it dry and away from water. Your chemical formula is calcium carbonate. Heat it forms calcium oxide plus carbon dioxide. If it's absorbing 178 kilojoules in the forward direction, in the reverse direction, it needs to release 178 kilojoules. Okay, and then last but not least, in order to calculate the mass of carbon dioxide created, you've got your calcium, carbon, and oxygen. So calcium carbonate, it's got a molecular mass of 100. Carbon dioxide's got a molecular mass of 44. So the number of molecules of calcium carbonate is 2.5, which is the mass of it, which was 2.5 grams, divided by 100, which is the total mass, and then multiplied by 0.2 which equals 0.25, sorry. So then we have 0.025 as the number of moles of carbon dioxide. So then we need to multiply the number of moles of carbon dioxide by the molar mass, which is 44. So 44 times 0.025 equals 1.1 grams. So you form 1.1 grams of carbon dioxide. So I hope you've enjoyed the video. As always, you don't need to submit your notes or your answers at all because you should have self-marked. And as I said, we'll check on Friday anyway when you're doing those SAM learning questions. And also I might have a physical look at your notes to make sure that you are doing it all. Okay, so as always, stay safe and I hope you have enjoyed.